So let's then start at looking at the first problem, first step. What's the value of a power plant from which you can actually suspend operations whenever the price of the input of the gas, in our case, is too high to warrant efficient production. So that's basically what this picture represents. So here you see one particular potential path of the price, the blue lines, it's moving up and down, of course. But when the price of gas, which is a cost from the point of view of this gas-fired power producer, when it gets too high, it's no longer profitable to operate this plant, because then the value of the electricity that you produce, which is A, is going to be lower than the cost of the gas that you burn to do that. So in all those periods in which P actually rises above this dashed red line, you will actually go and switch off this plant, while whenever actually price is still below this dashed line, you will actually be producing. So what it means in terms of the profit flow, that's over here actually, what these profits are is, whenever A is bigger than P, then A minus P is bigger than 0, then your profit flow is going to be A minus P, so the value of electricity, minus the price of gas. But whenever P is above A, then A minus P will be negative. And then we switch off the plant, and actually profit flow is going to be 0. So with this profit flow being the maximum of A minus P, what we're interested in is the total value of the project. So the total value of the project is going to be an integral, because we're running this plant from now until infinity. And what do we get? Well, in the future, at each point in time in the future, so this integral is over t, over time. So we're discounting, so this is this discount factor in continuous time. What do we get? Well, in each point in time, we get the expectation of that profit flow, is the expectation of that maximum of A minus P or 0. And the question is, if we want to know what the value of the plant is, we need to do this integral essentially. Now, is that easy? Well, let's have a look actually at what this means. So what was this profit flow? Pi of P is the max of A minus P and 0. Let me draw that over here just to get some intuition. So here's P. So whenever P is above A, the price of gas above the price of electricity, then we won't produce, right? And it's too expensive. So then the profit flow is going to be 0. But whenever P is below A, we're going to produce, and the profit flow is going to be A minus P. So that takes basically this particular value. So this is the form, this cusped object here is the form of this profit function. And perhaps you recognize this. And you might recognize this actually as the payout of a put option, of a standard European plain vanilla put option. So this is what a put option looks like. And actually we know what the value is of a put option somewhere in the future. So we know what the value is of a put option with maturity, say 1 year, so 1 year from now. And that value is actually given by a formula. It's called the Black-Scholes formula. It's a pretty complicated formula. But we know what it is. But we're asking something more. We're asking what's the value of a whole string of these put options, because we are not only producing electricity next year, but we're also producing it tomorrow and also producing it in 2 years, according to this payoff function. So essentially we have a whole portfolio, and we can interpret this plan as being a whole portfolio of Black-Scholes put options, one for each maturity into the future. And we're asking to add those up and to discount those. Well, that's a really daunting task. That sounds really difficult, and it is actually difficult. So if we are actually going to put in this Black-Scholes formula and going to do this integral explicitly, that's really hard. Well, fortunately, there is a backdoor here. And this backdoor is using the Bellman equation, and we are going to see that this is actually not that difficult. We can do it in basically perhaps in less than half an hour to finish this video, and we'll actually be able to compute through this backdoor, to this Bellman equation. We are going to compute this value of all the sum of all those Black-Scholes formulas without actually ever having to write down any of these single Black-Scholes formulas at any point in time. So this is pretty awesome actually. We can actually do a seemingly very complicated exercise involving Black-Scholes formulas, do this using the Bellman equation, and make this actually doable for us in a matter of half an hour. So let's see how that works. So there we are. So we're going to do this, and we're going to use the Bellman equation here. So how do we do this? Well, let's first look at the simpler problem. So the simpler problem here is, suppose we would never switch off this plant. So we're always going to produce. So what does that mean? We're always going to have a profit flow which is equal to A minus P, or in other words, the expectation of the difference between the electricity price A and the gas price, cost of gas, P. So we're even going to produce when gas price is really high at a negative profit margin. We're just going to do this as a benchmark. Of course, it's not going to be optimal, but let's see whether we can actually figure out what that would be worth. So the value of a plant that's always going to produce. Well, can we actually evaluate that? Yeah, so this, if you look at this expression here, this expectation of A, well, A is just price of electricity is constant, so that's always A. P is actually moving, but we know what the expectation value of P is, because it's moving according to this geometric variant motion, and we already know that at time t in the future it will have grown at this growth rate mu. So this is what the expected value of P is in the future. So can we actually use that to compute what this is? Yeah, of course. So this, if we plug that in, we have this value will in that case be this A, expected value of A, discounted, minus this growing P, growing at a drift rate mu, and again discounted at this discount factor R. So it's two different intervals, but we know these intervals, right? So this interval is just the perpetuity, the fixed perpetuity of getting the income from selling electricity at price A, and we're subtracting from that the growing perpetuity of having to pay for the price of gas all the time, which is growing at a growth rate mu. So we can evaluate those two intervals. We did that before already. First one, the straight perpetuity was just A over R, and this growing perpetuity P divided by R minus mu. We've seen all that before. So this we can evaluate. So we know what the value is of this plant if we would keep it on all the time. So without this suspension option, this value of Vg as a function of P takes this form. And so now we ask the question, if we can switch off the plant when this gas price P is getting too high, it's getting higher than the price of electricity A. So what is the effect of that? Or in other words, what is the value of that option to suspend the operations of this plant? So we're going to do that analysis, but it's also actually in the book, in Suspending in chapter 7. You might want to have a look at that as well, but let's do it. So let's use the Bellman equation to actually figure out what it is. So remember, if we look at the Bellman equation, we have to figure out in what regimes we are, and here we have two regimes. So one regime is when P is bigger than A, so that's when we will not be producing, so the profit flow will be zero. We have suspended operations, shut down the plant. So the Bellman equation in this case is just the Bellman equation with the cash flow term 0. So this is basically the Bellman equation. This is familiar terms here, but 0 where the cash flow appears. No cash flows when P is bigger than A. In the other regime, regime 2, when the price of gas is below A, we will be producing. So that's a production regime, and in that regime, profit flows will be A minus P. So here we again have the same Bellman equation, so these black terms are what we always have, and here again we have the cash flow term, and in this regime is A minus P. So what we need to do is to solve these two equations, first in their general forms, and then try to match them together to find the exact solution, basically, that matches up these two solutions nicely. So let's first look at the easier one, I guess, where P is bigger than A, so where we're not producing. So in this regime where we're not producing, we have no cash flows. So there we have a Bellman equation with a 0 over here, so no cash flows, so just these standard terms. And actually we recognize this equation because it's precisely the same equation as we already solved when discussing this waiting regime, right? So no cash flows here. We're just waiting here in order to switch it on again at some later date. So we know actually what the general solution here is. It was the sum of these power functions, right? With arbitrary coefficients b1 and b2. And we still need to figure out what these b1 and b2 is later. And these beta 1 and beta 2, of course, are again these positive and negative powers that we know. So this is the solution to the Bellman equation in this regime where we're not producing, where P, the price of gas, is above the price of electricity. So what about this in this other regime? So the Bellman equation for where the price of gas is below A, so in that regime we are producing, right? So we get a profit margin A minus P. So in this regime we have production, we have a Bellman equation where we have a cash flow term in each unit of time. We get A minus P. We get this fixed income from selling the electricity that we produce minus the variable cost P of buying the gas essentially to produce this electricity, and these other terms again are the same. So we want to solve this equation. So we can find a solution, find a function v of P that satisfies this particular equation. Now that's a sort of a hard, and again we want to find the most general solution, right? So that's a harder problem, so we haven't done that yet, but so we're going to tackle that now. So the first question we can ask is, even if we don't know the most general solution, can we find one particular solution? So just one solution, not the right one, not the most general one, which actually solves this equation. And I'm claiming that yes, we have one such solution. So let's go and look at that. So consider indeed this plant that we just looked at, which we're never shutting down. So we're always producing. We just figured out, oh, the value of that plant would be this perpetuity, A over R, minus this growing perpetuity, P divided by R minus mu. Now my claim is that this value in itself should also satisfy a Bellman equation for a plant which is always producing. Well, what's the Bellman equation for a plant which is always producing? Well, it's always generating A minus P, right? But this equation is precisely the equation that we're trying to solve. So my claim is, and indeed, we can solve this equation. We can find one solution. This thing over here, this object over here, should be one solution to this particular Bellman equation. So let's check whether that's the case, or let's see whether that's the case actually on paper. So we have this equation R times V equals A minus P plus then this drift term times the derivative plus this volatility term sigma squared times P squared times the second derivative of P of this function V. And my claim is, yeah, we can actually solve this by setting V of P equal to this perpetuity minus this growing perpetuity. That should solve this equation, because this equation also describes a plant which is always switched on, which will always have this term A minus P, and it's just one regime essentially. So let's check that. So if this is V, then V prime is, well, this thing does not depend on P, so that vanishes, but this second bit does depend on P, so we get minus R minus mu, and of course V double prime, this derivative of the derivative, is of course 0, because the derivative itself is just a constant. So does that indeed solve the equation? Let's check that. So let's just plug it in to see whether it this gives a correct result. So R times A over R minus R times P divided by R minus mu, that's the left hand side over here, plugging in this V over P, V of P, equals, its question, A minus P, it's A minus P, plus mu times P times V prime P. And V prime P is this thing, minus R, minus, and divide this by R minus mu, and the second thing here is 0, right? So does this hold? Well, let's see whether it holds. First of all, we can cancel out these R's over here, and then you see that the A over here actually cancels against that A. Let's makes it easier already. So the question is, let's multiply everything by R minus mu. Then we get minus R times P on the left hand side, And on the right hand side we have this p is minus p minus, I have to multiply again by r minus mu, so this gives me minus, this thing gives me minus r minus mu times p, and then the second bit, multiplication by r minus mu cancels out this denominator, so it remains as minus mu times p. So this, we can simplify this because here we have minus mu, or plus mu times p minus mu p. So these two cancel out. This one cancels against that. So this is going to be minus rp. And indeed, this solution, this function here, v of p, indeed satisfies that equation just like we would like to. Okay, so let's get back to the slide. So we have a solution. So this particular solution here actually is a solution to that equation. So we know one solution to the equation, but it's of course the solution which describes the times which is never switched off, so this is not the one that we are after. But perhaps you can use this one actually to generate all other potential solutions. And the point here is that we can actually use a useful fact here of differential equations, which is the following. So if we have one solution, this particular solution to this equation, so we have that, right? And that's what we just did. We figured out one solution. If we then also can solve that same equation, but now dropping the Cashflow term, so putting a zero here essentially, it's called the homogeneous Bellman equation. Then we get, that homogeneous Bellman equation is an equation that we know because it is weighting equation. And we actually know the most general solution to that because it's the sum of these power functions. So we have the most general solution to the homogeneous Bellman equation. Then the point is that the sum of this particular solution plus this most general solution will also solve our original equation. So let's see how that works in practice. So we have a particular solution, so we have this, we know that this v tilde, it is a solution, it's not the right one that we need, but it is one solution to this equation. We have the most general solution to the homogeneous equation, that's just the sum of the power functions with certain coefficients that we still have to pick, C1 and C2. Then the most general solution to the non-homogeneous, to the original equation, is going to look like the sum of this thing over here plus this most general solution over here. So this is the general solution to that particular, equation. So that's useful. So we now have solved basically, we're somewhere because we have solved basically what the Bellman equation looks like, also in this regime where the plant is actually producing. So in this left-hand regime where price is below the electricity price, we know we have the value function which looks like this, which has this production terms plus these option terms if you wish. And on the right hand side we have the regime in which there's no production, plant has shut down for a while, we only have these option and these weighting terms, right? B1 and B2. And we know that the boundary between these two regimes is where the price of gas equals the price of electricity. Above this regime we switch off the plant, below this threshold we switch on the plant. So what we want to do is figure out still what are the unknowns here, C1 and C2 and B1 and B2. So those we have to solve. So and of course we're going to solve those again by looking at the boundaries. So what are the boundaries? Well, first of all we have a boundary over here for this particular thing. At P equals 0, if the price of gas goes to 0, so what's the value of this plant? Well, if the price of gas is 0 and will remain 0 forever, we are always going to produce electricity at fixed income A basically, so the value should be the perpetuity A over R. So at P equals 0, the value should be A over R. So when does that happen? Well, P equals 0, plugging that in here actually gets rid of this term. The positive power, no problem, gets 0 as well, so this means A over R, but this thing means trouble, right? So P equals 0 with a negative power means a term that's blown up. So I want to get rid of that, so C2 must be 0. On the other hand, the other boundary occurs over here, P going to infinity. That's also a boundary. So the large P behavior with this thing. So what happens if the price of gas gets really high? Well, of course the plant is switched down, but if this price of gas gets towards infinity, we will never switch it on at all anymore. So the value of this option should actually go to 0 as well. So what does that mean? Well, this B2 is fine, right? Because P to the power of beta 2, so beta 2 is a negative power. So if we take a very large P, a very large number to a negative power, that goes nicely to 0. But now it's this term which gives trouble. This term is going to blow up. Infinity to a positive power, that blows up. We don't want that. So this behavior for very high P tells us actually B1 should be 0. So these two boundaries actually get us rid of these of B1 and of C2, so but we're still left with C1 and B2. So we still need to solve those. And of course we're going to solve for those by looking at what's happening at this threshold between switching on and switching off this plant, where P equals A. So there we demand again that these two solutions match up nicely. So what we need to do is we first of all need to make sure that their values match. So when we plug in P equals A, the left hand value, or the right hand value rather, which is on the left side here, it's awkward. So this B1 was 0, but switched off plant still has value B2 times P to the power beta 2. So if we plug in P equals A, we get B2 times A to the beta 2. It should match with the value that we get if we plug in P equals A on the other side, and that's this expression over here. So that's value matching. Values should match on left and right side at the threshold point where P equals A. Secondly, we have smooth pacing. So what was that? We need to take the derivative with respect to the price P, and then plug in P equals A. So it gives us the second equation, which again is the derivative with respect to P from the one side, and here's the derivative with respect to P from the other side, and then we plug in P equals A again. So it looks a bit familiar. So now we have two equations. We have two things which are unknown, the C1 and the B2. And of course, these are essentially two linear equations in two unknowns, and we can solve two linear equations in two unknowns. So let's do that. So let me do one of those actually on paper. So let me write down those equations again. So the value matching equation was this one. B2 times A to the power beta 2 equals A over R minus A over R minus mu plus C1 A to the power beta 1. And the smooth pacing condition was taking the derivative beta 2 times B2 times A to the power beta 2 minus 1 equals 0 from the derivative here, because this didn't depend on P. But this one had a P in there, so we took the derivative there. It gives us 1 minus 1 over R minus mu plus beta 1 times C1 A to the power beta 1 minus 1. So these are two equations in B2 and in C1. I want to figure out what those are. So what I'm going to do is, let me first figure out what C1 is. And in order to do that, and we have to eliminate, of course, the terms involving B2. And the way to do this, of course, is let me multiply the first equation by beta 2. Beta 2 times B2 A to beta 2 equals beta 2 times A over R minus beta 2 A divided by R minus mu plus beta 2 times C1 A to the power beta 1. And let me multiply the second equation by A. So what you notice, the nice thing is that make sure that these left hand sides are going to be the same. So that's going to allow us to eliminate actually this thing. And the right hand side I'm multiplying by A, so I need to do that over here as well. Minus, so multiplying this thing by A gives me that. Plus multiplying the second term by A gives me beta 1 times C1 times A to the power beta 1. So now these two terms here on the left hand side are the same, so I can get rid of those just essentially by subtracting these two equations. So then 0, subtracting these two, equals beta 2 times A over R minus beta 2 minus 1 A over R minus mu plus beta 2 minus beta 1 C1 times A to the power beta 1. Or in other words, C1, taking this to the other side essentially, is going to be 1 divided by beta 1 minus beta 2. So I'm taking this final term here to the other side, which gives me a minus sign, but I'm also interchanging the beta 1 and the beta 2, which gives me a 1 more minus sign, so those are cancelling, so I get just a 1 divided by beta 1 minus beta 2 times beta 2 A over R minus this object here, and I still have to cancel this one, so that means multiplying by A to the power minus beta 1. So this is what C1 is. And in a similar way, of course, we can also compute what B2 is, and you can do that yourself. So let's go back to the slide. So we did this, sorry, the first one essentially. So what's the value for the operating, in the operating regime? So let's have a look again. Value in the operating regime was, well, first these cash flow terms, if you wish, plus these option terms, in particular this first option term, which involves this C1 that I just computed, times P by beta 1. So that's what we see here, these cash flow terms, times the C1 that I computed, times P to the power beta 1. So the other blue stuff here is the C1 that I just computed. And if you do the similar computation, but just computing B2, then you find actually a similar expression here for the other side in the switched off part, suspended operations part. So it's the interpretation of these blue parts. Well, of course, the interpretation of this black part is just the cash flows, the value of the cash flows that you get if you were running forever. So what must this be? Well, this is the additional value that we get, the option value when we are in the operating regime and the production regime, of being able to suspend operations as soon as P gets too high. So this is the option, the value of the option to suspend these operations. And likewise, when we're in the idle regime, so when P is bigger than A, what's the value of the suspend? It's only option value, right? It's not producing right now, so no cash flows, but there is still some value, this value in particular, from the option, measuring the option to resume operations. And of course, both these options will be positive, right? It's nice to have those. It's a positive value. So you want to check perhaps that these blue expressions are actually positive. So the graphical depiction of this results is this. So on the left hand side, this value function looks like the blue line. On the right hand side of A, where P is bigger than A, it looks like these dashed red lines, and indeed they're matched together nicely at A. When P gets very small as 0, essentially we will only be producing electricity at cost 0, so then we have a value of a perpetuity of A divided by R, the price for electricity, the value of electricity divided by R. Whereas when price of gas goes really high, we suspend operations, but as price gets really far away, we cannot hope to actually switch it on anymore at all. So then the option value should go to 0, as you can see here. It does. And of course, this green dotted line here is what is classical values of this plant that we will never switch off. And it actually goes negative here. So what's the takeaway? So this project has a value even when it's not producing, so when it's switched off. And well, what value is that? Well, the option value of being able to resume operations in the future when P drops below A again. And on the other hand, when price is below A, there is also additional value above the classical value, and that's the option value of being able to shut down the plant when P might get above A at some point in time. And finally, the larger the uncertainty sigma, so sigma appears in this beta 1 and beta 2, you'll find that these option values are actually going to be greater. So the larger uncertainty, the larger option value, meaning that these lines basically will go up in in the graph. So that's our step one essentially. So we figured out what's the value of this electricity, this gas-fired electricity plant, once we've built it. So now we take the next step. Suppose we have the option to build this plant, but we might wait a bit. So still forget about the biomass plant, but we can invest in the gas-fired plant. What's that option worth, and when should we invest in that case? So that's the intermediate step that we'll do next.